This video tutorial describes how reactive conformation models can be developed for explaining and predicting stereoinduction in the context of the diastereoselective reduction of a chiral ketone. This was first observed in the reduction of the chiral ketone with lithium aluminum hydride to give a 3-to-1 mixture of diastereomers. The diastereoselectivity can be enhanced by reacting with a sterically more hindered and slightly less reactive lithium trialkyl borohydride reagent. To develop a reactive conformational model for these results, we construct a Newman projection. I like to do this by imagining orienting myself looking down the axis of the carbon-carbon bond from the functional group undergoing reaction to the chiral center responsible for stereoinduction. From this orientation, the phenyl group is at the top of the Newman projection. The methyl group is to my right, and then the small hydrogen substituent is to my left. You can see how these are oriented with the large, the medium, and the small substituents. The reactive conformation model, proposed first by Hugh Felkin and then developed more extensively by computational studies by Nguyen Trong An, has the carbonyl group perpendicular to the large substituent. The carbonyl can be oriented in one of two directions, to the right or to the left. The reaction of the carbonyl is activated by coordination to the Lewis acidic lithium cation, and then the nucleophilic trialkyl borohydride adds to the carbonyl by the Bürgi-Dunitz trajectory, corresponding to nucleophilic addition to the pi star antibonding orbital of the carbonyl. From the structure on the left, the trialkyl borohydride reacts closest to the small hydrogen substituent, whereas the other conformer on the right has the trialkyl borohydride reagent reacting closer to the medium-sized methyl substituent. The selectivity results from relative differences in the steric hindrance, adding adjacent to a hydrogen versus a methyl group. You can see the transition state as bond reorganization occurs from the trigonal planar carbonyl to the pyramidal alkoxide. After aqueous quench to give the alcohol, you can see that the chirality does not match that of the like diastereomer, but rather corresponds to the unlike diastereomer by bond rotation around the sigma bond. Between the chiral centers. On your own, practice creating reactive conformational diagrams, as depicted on this summary slide.